Okay, so in this video, we are going to consider how to calculate the variance in raw data. So far, like as we did in chapter 3, at the time, remember, we defined the mean as the sum of probability weighted outcomes. And as a special case, when you don't have the probability distribution table, but only have observations, only have the data, then you may treat the data as equally likely outcomes, and so you are going to weight them with 1 over n. So then you could get the formula, the average formula you are used to, right? So we are going to get a similar result here, but there is another difference in unique in the variance. So we are going to end up with two different formulas. I'm going to explain them, show you how they are different, and then we are going to Microsoft Excel and see how we can implement them. Okay. So in this video, the example we are going to consider is a firm's revenues seasonality. So firms report their revenue every quarter, and some firms, depending on the industry, some firms have seasonality. Like some firms do better in summer, or other firms do better in winter. Depending on their nature of their industry. So, but like here, let's think about a firm that has four observations, that gives us four observations, the revenue, the sales in each quarter, right? So $76 million in the first quarter, 82 in the second quarter, 80 and 74 in the following quarters. So we are going to consider these four numbers as a sample. So there are only four numbers for simplicity. So then let's calculate the variance. The first thing you have to do is to calculate the mean. So I'm going to skip that. It is pretty simple. Just add four numbers and divide by 4. It is pretty straightforward to calculate the mean. And then, as we did before, we are going to calculate the deviation by subtracting the mean from those outcomes, those observations. So we have four numbers, and from them we subtract 78. So that means in the first quarter, the revenue is $2 million below we expect, and in the second quarter, $4 million above, and like 2 plus 2 minus 4. So like that, we have deviations. So because we have four observations, we have four deviations. So deviation is a transformation of the random variable. So there are equal number of deviations as the sample size. And then the next step is to square the deviations. So minus 2 squared equals 4, and 16, 4, and 16. And as you see, plus 4 and minus 4 are equally distant from the mean, so their distance, the square deviations, are the same, right? So we have 4 square deviations. We are going to take the mean of these squared deviations. That is the variance. That is the definition of the variance. So calculate the mean of these numbers. That is, the variance is 10, right? This is how you can calculate the variance according to the definition. Okay, so nothing special. Like if you understand how to calculate the square deviations and how to calculate the average, then you are good. But there is a weird convention that there are two different formulas to calculate the variance. So one is exactly what I just did. Use this formula. So xi is ith observations. For each observation, subtract the mean and take square, and then sum, and then divide by n. exactly this is what I just did, and kind of natural formula, right? However, in practice, a lot of people use the sample variance formula. The only difference is in the denominator. Instead of dividing it by n, the sample variance formula uses n minus 1 as the denominator. So this is pretty weird. Why, when we take the average of the square deviations, why do we use n minus 1? So it is not easy to explain this right now. We are going to review this problem in chapter 8. Simply speaking, the main reason is because when we subtract the mean is already calculated from the data. So in some sense, because we already calculate the mean, so our sample size was n. But when we calculate the mean, we consumed one of the information. We had n observations, but one of them theoretically has been consumed as in the calculation of the mean. So when you calculate the squared deviations, basically there are n minus 1 remaining informations. So that's why we are using the denominator n minus 1. So I'm just roughly explaining the mathematical intuition behind it. So we are going to come back to this problem in chapter 8 when we think about that problem. So this is the data I used in an earlier example. So 10-year Treasury note yield and S&P 500 index return monthly from January 1985 through 2022 December, right? So I'm going to show you. So if you want to use variance formula, if you type variance, or there are two different formulas, var.p and var.s. These two are variance formulas, and P stands for population, and S stands for sample. So let me just try what happened. So I used population variance formula, var.p, and I entered Treasury note yield. Then you see the variance is 6.085. That is the population variance of Treasury note. Similarly, let's see sample variance. Let's see what happens with sample variance. So var.s and enter this data. Then you get a very similar but slightly different number. Right? The main difference is, as I said, the sample size is, we have 456 months. 456. So the population variance uses 456 as the denominator, but this one uses 455 as the denominator. That causes the difference. So just to see that, if you multiply their denominator, you see the sum. This is the sum of square deviations. They are the same. So if you multiply the denominator, then you will get the same number. So same thing. Let me do this for the S&P 500 return. S&P 500 return has a variance greater over like 3,000. So the variance of 10-year Treasury note was 6, but it is 3,600. Huge difference. But as I said, variance does not preserve the scale. The scale of the variance can be inflated or deflated, so it is not an exact comparison. Like you cannot say this is like 600 times larger than the 10-year Treasury note. What I recommend is standard deviation. Standard deviation formula in Excel is STTEV. STTEV has also two different formulas, .p or .s. .p is population standard deviation. So I calculated standard deviation based on the population formula, and let's try sample standard deviation. Also, they are similar but slightly different, right? This is population standard deviation formula, and this is sample standard deviation formula, right? And thus, just to verify, I use this formula. We already calculated the variance, so by taking square root, we should be able to get the same number. Let's see if it's the same. Yes. So standard deviation formula should be, as it should be, is the same as the square root of the population. I mean the variance. Or if you use sample formula, sample standard deviation is the square root of sample variance, and population standard deviation is the square root of population variance formula. So it's nothing surprising. There is nothing surprising. So variance was 6 something, but actually the standard deviation is 2.4%. So this is interpretable unit. And similarly, if you use the S&P 500 data, then the standard deviation is about 60, which is square root of these variances. So the standard deviation of S&P 500 is 30 times larger than that of 10-year Treasury note yield. That makes sense because both are in the same unit in percentage. So this is how we calculate the sample, how we calculate the variance from data, and how we interpret them. Okay. So as I said, back to our example, I did not finish this. So in our example, the difference between population variance and sample variance is larger when the sample size is small, because the difference between 4 and 3 is like say 25%, but like in our data, when we have 456 observations, like subtracting 1 or not does not cause much difference. So in general, in our data, real data, we have large sample size, so both formulas are not that different. They are pretty much the same. So you don't need to worry. You don't need to worry about what you are using. So just choose whatever. But in general, the sample variance formula is more common. It is accepted as kind of the norm. And as I said, more details will be discussed in chapter 8. At that time, we are going to use this as an example for an estimation problem. Okay, so this is the summary. This is how you calculate the variance. Nothing special, but in the last step, you have to make a choice. But it doesn't matter what you choose. If you just want me to recommend one, use n-1. But using n is not a problem. Okay, so and I will ask you to do this as an exercise. Suppose that there is another form which has a larger seasonality. So in summer, it has much higher revenue than other quarters, but in winter, it has much lower sales than other quarters. Like say, think about ice cream company, company will do much better in summer, but not that much in winter. Okay, so do some algebra and see. By the way, I specified you need to calculate the sample variance. Use the sample variance. Okay. Okay, let me show you the answer. First, you need to calculate the mean. And there are only 4 numbers. It should be pretty easy to calculate the mean, which is 75. So once you get the mean equals 75, then kind of mechanically you just subtract the mean from observations and then square the deviations. And you are going to get these 4 squared deviations. 4, 400, 4, 400. And then you calculate the variance as the average of them, but when you calculate the average, you have to use n-1 as the denominator because we are calculating the sample variance. Sample variance uses 3 as a denominator, which is 269. If you want the standard deviation, you can take square root, but excuse me, not in this exercise. Okay, so this is the end of the discussion on variance and standard deviation. Okay, and finally, in the final few slides, I'm going to discuss additional measures. So far we basically learned two types: measures of central location, measures of variability. Measures of central location include mean and median. And additionally, we learned percentiles as a non-central location. Also, in chapter 4, we learned range, interquartile range, and variance, standard deviation. So these two are two major categories of summary measures. But there are additional measures that captures like different aspects of the distribution. So that's what I'm going to explain right now. A third measure. Mathematically, you may understand the variance as the mean of squared deviations. Like if you mathematically generalize it, you can think of cubed deviations. Instead of just taking square, raise the deviation to the exponent of 3. Right? So multiply deviation one more time and take the mean. Basically, the process is the same, replacing exponent of 2 with exponent of 3. And then we call this skewness. So this measure is skewness, and what it captures is it captures the symmetry of the distribution. If the skewness is 0, then the distribution is approximately symmetric. But if skewness is positive, that means there are outliers on the right tail. So there are outliers that are exceptionally greater than like typical observations. Okay? But if the skewness is negative, then the other side. Outliers are on the lower side. So there are outliers that are especially smaller than typical observations. So this is, if you use a third measure, then skewness is usually the third one. So the measure of center, measure of variability, and then measure of symmetry or asymmetry. Okay, this is the idea. So visually, if the tail is long on one side, longer than one side than the other side, then we say the distribution is skewed to that way, right? So this example on the left panel, we say the distribution is left skewed or negatively skewed, or tail is long on the left side. And borrowing the result we learned in chapter 3, you could expect the mean is smaller than the median, right? Because these outliers will lower the mean more than the median. Exactly flip like it does. So symmetric about 0 center, you are going to think about right skewed distributions. Outliers on the larger side, and then we say positively skewed, a long right tail, and then mean is greater than the median. Okay, so these two different shapes can be captured by skewness, which is a measure of asymmetry. And another measure, mode. In textbooks, in typical textbooks, mode is considered as a measure of central location. But frankly, I have never seen this as a measure of central location in any context. So I don't include this as a measure of central location, but it has its own role. It's another interesting measure and can explain things. So statistically, the definition of the mode is like this: the most frequently occurring value, right? So textbooks use this as a central location, but I disagree with them. And graphically, what the mode is literally the peak. If you draw a histogram, the highest point is where the mode is. Mode is where the histogram is has a peak, right? Mode is here, mode is here, mode is here. And then we usually use mode to describe peak, right? So these examples are called unimodal. That means there is only one peak. So that's unimodal. And maybe you have heard about bimodal distributions. Bipolar distributions have two peaks like this. So you can think of this as a mode and another mode, right? Just simply there are two. You can think them as like two different peaks in their histogram, and if you can imagine like a histogram with even more peaks, like then we say multimodal distributions, which is really rare in any data, but theoretically possible. Multimodal. So mode is to describe the number of peaks. Usually we use mode to see where are peaks and how many modes there are. And finally, this is another extreme. There is no mode. There is no peak. Overall, it is stable, like flat, across all the possible outcomes. Then we say the distribution is uniform, right? So, like a typical example is rolling a dice, flipping a coin. They are uniform. So that is that these are kind of additional extra measures. And finally, before closing, I'd like to show you a quick data analysis tool. So if you click Data tab here, and then you will be able to see data analysis here. Click Data Analysis, and then there are many options. But we will use descriptive statistics option. Descriptive statistics. That's what we just learned. And click OK, and choose to data. I included 10-year Treasury bill in S&P 500, and check labels in first row. I will check here summary statistics. I'm going to summarize the data by clicking this, and if you click OK, then takes time. You get a new table. This new table shows many summary measures. So what we learned, mean. If you compare mean, as like Treasury note is 4.8, but S&P 500 is 23. By the way, the reason why we have different mean here is because usually financial return should be calculated as a geometric mean, geometric average. But here, this mean is arithmetic mean, so not exactly correctly calculated financial mean. And standard error is a kind of standard deviation, but standard error is standard deviation divided by sample size n. So that is the definition of standard error. Standard error. So let me increase the font size. And median, we learned median, and mode, we learned mode, but there is no mode in S&P 500 because it's too volatile. So there is no same number occurs twice or more times. So there is no mode. It's interesting. And standard deviation is calculated here. So let's see. Standard deviation is 2.4696. That is this one. So these numbers are included, and note that these numbers are sample standard deviation, not population one. So the denominator is n-1. That is used here. Okay? And to see if the standard error is calculated correctly, you can divide this by sample size. Excuse me. Divided by square root of n. So if you divide the standard deviation with square root of the sample size, then you are going to get this number, standard error. So standard error is standard deviation divided by square root of n, which we are going to learn in chapter 8 or so. So wait until there. And sample variance. Variance is calculated. We know how to do it. Skewness is the mean of the cubed deviations, right? And kurtosis. Kurtosis is really rarely used measure. This is a fourth order measure. So if you square deviation, you get variance. If you cube the deviation, then you get skewness. If you raise the deviation to the exponent of 4, you are going to get kurtosis. This captures the thickness of the tail. So, but it's not commonly used, so I will skip that. And range is exactly the range we calculated. Sum is sum, count is number of observations. So, in the last two chapters, I have quickly reviewed many measures. And as I said, these measures summarize the shape of the data, the properties of the random variable. So I hope these help you, like when you analyze data, maybe by looking at these measures, I hope you to understand the data better. So you should be able to understand what they mean and what you can interpret from them. Okay. Okay, thank you for watching. By the way, I did not explain this. So skewness, look at the skewness. Skewness of 10-year treasury note is close to 0, but it is much larger. So anyhow, both are positively skewed, which means there are extremely large values in our observations. So that's how we interpret skewness. Okay, thanks a lot. And we are going to finish chapter 4 here. Chapter 5 will be slightly different and kind of is more difficult. So make sure you understand everything so far, and see you in the next chapter, next video. Thank you for watching.